So you need to know about metallic bonding, and you do already. And I think you know from what you told me in our little rehearsal there that we described the structure as a giant metallic structure, and anything with a giant structure, we learn even as low as year 7 nowadays, if we've got a giant structure, we tend to have a high melting point. The metals, there's a lot of metals and they vary quite a lot, and we all know that mercury is a liquid at room temperature, but compared to say simple covalent substances that got high melting points, and some metals have very high melting points, of course. Tungsten, I think, is somewhere around 3,000. Maybe that's not quite as high as that, but it's a very high melting point. And that's because you've got, again, this giant structure, lots of strong metallic bonds. And you've got a lattice structure. Which requires lots of energy to overcome. So nothing new there from what you've done and knew really well at GCSE. So we've got lots of strong metallic bonds, require lots of energy to overcome. So typically speaking, they're at high melting points. We all know that metals conduct. We've known this since primary school. So metals conduct electricity and heat well, but can we explain why? Now, best thing we can do to explain it is to talk about the structure first. And it's going to look very much like GCSE, and we'll advance it on a little bit in a moment. But what you've got, as Oliver described, is you've got a lattice. I'm going to draw it 2D, but of course in reality it's 3D, of positively charged metal ions. So, lattice of positive metal ions, and these are surrounded by a sea of delocalized electrons. So if you've got, say, a group 1 metal, there'd be 1 electron per atom. In other words, the one that's in the outer shell is delocalized and not fixed in place, and therefore contributes to the conductivity, thermal and electrical conductivity. And so surrounded by a sea of delocalized electrons, and that leads to electrical conductivity and you probably get away with saying something about delocalized electrons, but the GCSE answer is pretty perfect, so why not use that, which is that delocalized electrons kind of flow through, not throughout, but we're kind of implying they go from one place to another. If we've got a potential difference in the metal, they flow through the structure. So the negative electrons will travel towards the positive terminus, the power supply unit. So electrons can flow through the structure, through the metal, and carry the current, carry the charge. And they've also got thermal conductivity, very high thermal conductivity. So high and high. And again, we've got delocalized electrons. And these can flow, I'd say, throughout the structure this time. They can move around um, can throughout the structure, throughout the lattice, if you like, or just put structure, and transfer thermal energy. So those electrons can carry that energy around. Okay? Give you a chance to catch up a sec. There are some more general points I'm going to make about metals before I get on to me dealing with the question I just put to you. So we've talked about metallic bonding. I just want to really highlight to you here that we've got that lattice of positive ions, we've got surrounded by a sea of delocalized electrons. But the thing that maybe I didn't really emphasize here is that there's electrostatic attraction between the electrons, these delocalized electrons, and the metal ions and the positive ions. Right? That's what holds it together, which I didn't really make clear. And we'll talk about, I think we talked about a bonding continuum last time between ionic and covalent. We'll talk a little bit about metallic character and covalent character, all that kind of stuff next week. So we'll get onto that. But there's the other sort of general point about metals, which of course you said, but I didn't write down yet, was that they're malleable. And the other word we learned at GCSE was ductile, which means it can be pulled into a wire. And the reason why is because they're layers of atoms, or layers of, let's call them atoms, like this, layers of atoms or ions, if you like, can slide over each other without the metallic bonds breaking. And that's because those delocalized electrons can flow. As you bend the metal, the electrons just move to move around. So that kind of works really nicely. And one way to kind of consider that, and I will send you some nice slides on this, is worth realizing that as opposed to covalent bonds, metallic bonding is non-directional. In other words, the electrons are all attracted to all of the metal ions in every direction, non-directional. And that allows you to understand the malleability and ductility. It's non-directional metallic bonding. All right? So those electrons are like glue between all of those metallic ions. And I've got a nice picture here which I'll show you and I'll send to you by the Google Classroom. So I think we've covered lots of stuff here. I'm not going to tell you uses of metals because you know uses of metals. But I did say that I'd talk to you about the factors which affect metallic bond strength, leading into the stuff you'll do with Mr. Craig on periodicity, which I'm sure is covered in there as well. But let's do it now because it's an important idea. It's quite difficult too, I think. Oh, hard to remember anyway. Just get a bit of paper and talk about metallic bonding and strength. And you were part way there, so you had a guess at the answers. We're going to have a little chat just then. But let's look at that in a bit more detail. So we're going to do Group 1 versus Group 2. So we're going to do Mg versus Na. Group 2 versus Group 1. So magnesium has a higher melting point. And then sodium has a lower melting point. And therefore, we know that just empirically, we've seen sodium melting when we've chucked it onto water in the past. And we can look up the numbers. Melting point of sodium is 98. And magnesium is 1090. That's not insignificant. Oh, look, it's not as well. It's 650. So it's 650 melting point for magnesium. The boiling point was 1090. So significant difference between those, and that same pattern follows, for example, between potassium and calcium, rubidium and strontium, right? Same sort of idea. So it must be, because when we melt these substances we overcome the metallic bonding, it must mean, therefore, this has got a stronger, or there is stronger metallic bonding. This has got weaker metallic bonding. Now, you need to be able to explain that fully. So let's have a think about what's going on. So, as you already said when you were talking about this, that there are two delocalized electrons per magnesium, and here we've got one delocalized electron per sodium, and that's because magnesium is in group 2 and sodium is in group 1. And so twice as many delocalized electrons means stronger metallic bonding. That's only part of the story, and I've seen this particularly, remember an A-level question where this was worth 4 marks, this question. So you can't just run away from it with 1 mark, and that's part of the story. When you take those 2 electrons off magnesium, you end up with a 2+ ion. And if you take that 1 electron off sodium, you get a 1+ ion. And so not only have you got twice as many delocalized electrons, they're being attracted to ions which have a greater charge. And so the attraction is greater. So it's a double factor, second factor. So having twice as many electrons and twice the charge of the metals, the attraction, metallic bonding is stronger. But there is a third effect as well, which gets you the 4th mark if you like. So we've got 1 mark, 2 mark, 3 mark, potentially 4 marks here, which is that magnesium ionic radius is smaller. We'll talk about the reasons why in a minute, and again Mr. Craig will cover this with you. So it's not obvious why. The ionic radius is, according to the sheet I've got in front of me here, 72 times 10 to the minus 12 meters, 72 picometers. And sodium ionic radius, or radius of the ion, is larger. It's not obvious until you've done periodicity why that would be, and it's 102 times 10 to the minus 12 meters, 102 picometers. So why on earth would magnesium, or magnesium ions, which by the way have 10 electrons, and sodium ions, which by the way also have 10 electrons, they're isoelectronic, they have the same number of electrons, because sodium had 11 and lost 1, magnesium had 12 and lost 2. So why on earth, given they've got the same number of electrons, they've got the same number of shells, why would magnesium be smaller, magnesium ions be smaller? Discuss while I pause the video, and then I'll tell you if I can make it pause. Where's my mouse gone? Where's my mouse gone? You see it? Oh, there we are. Chemistry's all electrostatics, remember? It's all to do with electrostatics. So, yeah, exactly right. So, magnesium, the reason that magnesium ions are smaller, they've got the same number of electrons, is this has got 12 protons, and this has only got 11 protons. So when you're justifying lots of the stuff in the topic, Mr. Craig, that's about to come, you talk about number of protons, number of shells, and you can explain loads of stuff, like why atoms get smaller across a period, why ions get smaller across a period, provided the ions are isoelectronic. Okay, so that means that all of the stuff here that I've said, it makes sense. So you've got stronger metallic bonding, so you've got higher melting point. Let's just talk a little bit about transition metals. We will come to transition metals later in the course in details. Transition metals, and transition metals essentially the same as what we've been talking about so far. But there are electrons not that come from S and D orbitals. So S and D orbital electrons can be delocalized. And so we've got really quite an electron-dense sea of electrons, if you like. So that explains very high melting points and greater conductivity than there is in group 1 and 2. So we've got more delocalized electrons. We've got, generally speaking, there are some exceptions to this, but generally high melting points. And we've got, generally speaking, high conductivity. So lots of things that we use, like copper for wires, have got very, very conductive because we've got lots of delocalized electrons. And that's because you've got greater electrostatic attraction for all the reasons we've just talked about. Okay. Typically high density as well. Again, if you've got those transition metals have bigger nuclei, and they're quite dense compared to the alkali metals. And that's kind of it. A few bits and pieces there. We're going to talk about alloys and some other materials next time. We're also going to talk about something called the Van Arkel bonding triangle, which would be nice next week. And then we're nearly done with this topic, but I will give you lots of practice questions before we're done. I have set you, I believe, a homework on something which is quite short homework, I think, but I'll give you more to do next week on this stuff. Thank you, everybody. Bye-bye.